Well, I hope you enjoyed my last video in Malta. As is usual with these things, when we get back a holiday, we often plan next year's holiday, or at least think about it. So we thought about a cruise. So I checked on the internet, and no sooner did I start checking on the internet than I discovered all these stories of people jumping off cruise ships and into the sea for a bit of a laugh, with various results, not all good. And I wondered to myself, well, if they knew the speed on impact, that's how quickly they were travelling, would they be keen to do it? And can you work that out in the lab or in a home? Well, yes, you can. What I'm going to do, I'm going to assume they're jumping from a height of 30 metres. How quickly will they be travelling, or what speed will they be travelling on impact with the sea? Well, of course, I can't do the experiment. I can't film that, so I'm going to film a shorter version of it. I'm going to film this penguin falling 30 centimetres into a vase of water, and as it falls I shall film it, and my camera shall be set at a frame rate of 60 frames per second, which means I look at the film back and I move through every frame. I will know from the image how far the penguin has fallen, and on my camera I will know how it's fallen that distance in a 60th of a second, so I can work out its average speed during that time. I'm interested in the speed and impact with the water after 30 centimetres. When I work that out, I'm going to multiply it by 100 to find the speed at which something would be travelling at after falling 30 metres. Remember, 30 centimetres is a 100th of 30 metres. I'm assuming that that will give me the answer. Let's see how we go on with that then. 2.34 metres per second after 30 centimetres. If my assumption is correct, that will be 234 metres per second after 30 metres. Remember, 30 metres is a 100 times 30 centimetres. We've got a problem though. 234 metres per second, that's over 500 miles per hour. That's too fast. That's far too fast. Now, 30 metres, that's actually less than half the length of a football pitch. Now if you fall that length, from that height, you're going at a seriously high speed. Certainly you're going at a seriously high speed, but you're not travelling at 500 miles per hour. That's the speed of an aircraft. So what we're going to do now is, let's analyse the motion further, and we'll draw the obvious graph, which shall be height dropped versus time period, and the time period will be 1/60th of a second, the frame rate of the camera. Let's go and see how that works. This graph is an exponential graph. You would expect that, because in each subsequent time interval the penguin is getting faster and faster and faster, and therefore it will travel a greater and greater distance, and the graph reflects that. But now our job is to see if this graph corresponds to any graph that we know. So I've used my online graphing calculator, Desmos, to draw these 5 graphs, exponential graphs. As you can see, they're all of the form s equals kt to the power n, therefore our graph has to be of the same form. Question is it s equals kt to the power 2, s equals kt to the power 3 or what have you. Now I'm going to choose s equals kt to the power 2. That means the k has to have units of acceleration, because each side of the expression has to be dimensionally consistent. So I know for a fact I've got meters on the left hand side, therefore on the right hand side I must also have dimension of meters. Now t squared is seconds squared. I have to multiply that by ms to the minus 2 to get to meters. So I know my k has to have acceleration, has to have units of acceleration, although I don't know what the value will be. So what I'm going to do now, to find out the values, I'm going to assume it's t squared. I'm now going to find out the value k, and to find the value k, all I have to do is divide each pair of values that I worked out earlier, and that will simply be distance divided by t squared for them all, and we'll see what we get. Now you can clearly see from the table that the most common value is 490. 490 centimeters per second per second. That's the same as saying 4.90 meters per second per second. 4.9 meters per second is exactly half the acceleration due to gravity. So my constant k is half a. So if displacement is equal to 1/2 a t squared, it directly follows, after a wee bit jiggly pokery, it directly follows that v is equal to the square root of 2as. So v is equal to the square root of 2as. This means n is equal to 1/2, and the constant is equal to the square root of twice the acceleration due to gravity. I can read directly from the graph what the speed will be if I fall 30 meters, and you can see it's 24 meters per second approximately. Now, earlier on in the video, I multiplied the 2.4 by 100 and got a speed that was too fast. I should have multiplied it by the square root of 100, which is 10, and that would have got me the right answer, and that is the pattern that clearly emerged. Why did the graph seem to tail off when you cover a certain distance? Well, when you cover a certain distance, remember, you're getting faster and faster and faster, so you're accelerating for less time. So if you're accelerating for less time, you're not going to pick up as much speed in subsequent space intervals. Now, when you do have a formula like this, you can put in different values for A, and you can get different graphs. And here I've did it for two other planets in the solar system. Mars, which has got an acceleration less than Earth, and Jupiter, which has an acceleration greater than Earth, and you can see yourself the pattern that emerges there. Now, we haven't decided quite yet if we'll go on a cruise next year, but there is one thing for certain. If we do go on a cruise next year, I certainly won't be jumping off it. You can be assured of that. Thanks for watching. You're Scottish Physicist.